When looking at an aeration system, we need to be able to understand the differences in the geometry, the performance, the operations, and all of this affect the longevity of the installation and the performance, the maintenance of the installation, and the history of performance over time. Now, doing diagnostics requires to understand first how the aeration systems work, and then we can go and inspect them and understand little details about what can extend their useful life. So first of all, let's look at a quick survey of the type of aeration systems. The aeration system could be surface aerators. These are mechanical, they splash the water up in droplets up in the air. It could be diffused aerators, which are on the floor. It could be large bubbles or small bubbles, but these require a blower with an air line that delivers the air to these diffusers. Okay, could be a combination of both. We have turbines, for example, that take the air blown by a blower, and with a mechanical propeller, they shear it into tiny bubbles. That's also a possibility. So all of this exists. However, diffuse aerators are the most common ones for municipal, and so those are the ones you see the most throughout the whole course. Surface aerators could be high speed, low speed, vertical shaft, horizontal shaft. There are different types, and obviously depending on the application, one will have to look at how to narrow it down. The high-speed ones, it's a direct drive. There is a motor and directly a propeller, and it looks like the propeller of a boat. The low-speed ones, there is a motor, a gearbox to lower down the RPM, and then there is a propeller. You cannot have a high-speed one that is too big, otherwise it will be impossible, really, because the blade will have to be way too large. So the high speed ones are tiny compared to the low speed ones, which are very big. Diffuse aeration systems could have coarse bubbles or fine bubbles. The coarse bubbles are released by orifices that are usually 1 to 3 millimeters, or it could be usually the coarse bubbles are 3 millimeters or above. The size of the opening sometimes is 5 millimeters, sometimes is 1 centimeter, or it could be a slit. Okay, so you can release bubbles as large as you can handle. The fine pore diffusers are much smaller. Okay, so it's like a tenth of a millimeter, the size of the pore, and the pore releases bubbles that are 1 to 3 millimeters at the point of release. By the time it surfaces, it's much larger, of course. And the membrane can be punched, or it could be a porous stone. Sintered plastics existed in some applications in the past. I'm not aware of them still being on the market, but perhaps they exist in some installations. So those will be a solid type of diffuser rather than an elastic type of diffuser, more like a ceramic. The bubbles have a distribution, a size distribution. Obviously, they're not all the same. The more you go to the porous type of material, like a ceramic or a sintered plastic, and the broader is the size distribution. And the ones that are perforated or punched, they have a much more confined bubble size distribution. And you always have a full floor configuration for fine pore diffusers. The early installation of coarse bubble diffusers, they were probably closer to a spiral roll or a side installation where you had only one side of the tank with the diffuser, so the bubbles would just create this swirl. There was normal to the plane of the normal plane compared to the direction of flow, and all of this induced different type of hydrodynamics inside the tank. A surface aerator has this type of arrangement. It floats in the middle, and if it's low speed, it will have motor and gearbox. You see them there on the top, and it splashes there is a draft tube. The water goes in from the bottom and splashes the little droplets up in the air, and they land. The droplets, by traveling in the air, they get oxygenated. By the time they land, they're almost saturated. But the oxygen disappears very quickly, it gets consumed. So you have the bottom part that is possibly anoxic, and the top part that is fully aerated. Now that gives you a DO gradient, which is truly undesirable if you have to separate by settling, because you have possibly some denitrification occurring in your sludge, or some simultaneous nitrification, denitrification. The advocates for this technology will be those who don't have to worry about a power bill because it's energy inefficient, and also who don't have to worry about aerosols. If you're in a windy area and you're close to inhabited areas, you have a lot of aerosol being sprayed about, and it's an issue. The other problem you will have with this is cooling, because the droplets traveling in the air evaporate a lot of water, and that cools down the wastewater. So if you're in a winter climate, this may not be desirable. But if you're in a warm climate where you actually desire to cool down the water, otherwise you couldn't nitrify, this could be an option. Also an option will be coarse bubble diffusers. And these are, in areas where you can never dewater the tank, these provide good mixing all the way to the floor. All the maintenance is done, as dry maintenance is done on the dock where the diffuser is anchored, so you never have to empty the tank. But it comes with a DO gradient issue. And it's practically what it does, it pumps in a circle. So you always have the DO gradient. You can't do without it. You might have some issues if you do not have the DO, the dissolved oxygen, to be sufficient at some point. So that's something to be kept in mind. If you have lagoons, oxidation points, these were the typical applications for surface aerators in the past, but a lot of those have been decommissioned or converted into diffuse aeration systems. Also, if you place it in a lagoon, on a float or on a dock, and the lagoon is too shallow, it ends up scouring the floor of the lagoon. That's not good. And so that's an issue. If you have little pebbles inside the lagoon for any reason, those will become like bullets once they propel by this propeller. So that's another issue. And when you have a very deep tank instead, some of these tanks were like as deep as 10 meters, built in the 70s, where there was low surface available, land availability was scarce in some lots where treatment plants were sited in urban areas. So they will do the deep shaft type of arrangement. That requires a guide draft tube, otherwise you end up having vortices, and you end up having a recirculation that is confined to the area of the propeller. And the low-speed aerators are more efficient than high-speed ones. They have larger rotors, but they require structural elements to hold them up, because they're very heavy due to the motor and gearbox assembly. It could be tons of weight. So that's one of the issues. And also they usually they're manufactured upon order, so it takes longer to get them delivered. They're very typical for high purity oxygen tanks, the ones that are very common in very large plants from the United States and Canada, like legacy plants, and they typically are deep too. But these are some examples. On the left there you see the deep shaft aerator that has two blades to prevent the vorticing, and also the structural columns to hold up the pier also act as a baffle. And when they're in operation, you see the spray on the right. It's an undesirable amount of aerosol, of course, and you're going to have a lot of odor release there. Instead, these are like the high-speed float aerators. They have like a donut type of float, and in the middle of it there is the direct drive motor with the surface aerator. It's an inexpensive way to aerate. You need a lot of them. If you have a large lagoon, you see in the picture on the upper right, there is an aeration area, and then there is a zone where the scum is collecting, and it's not aerated until the next one. So there is an art in trying to locate them, but you always have gradients of high DO points and very low DO areas around it. And if you have, due to the high-speed nature, if you have any pebble there, it hits the propeller, that's what happens. So that's the first thing to diagnose is you're going to have very poor performance if you have a propeller all chewed up by hitting solids into the lagoon. Horizontal shaft surface aerators are the ones that are like brushes, and they had a market share in the lagoon area, in the lagoon space for a long time. The issue is that they have variable power, because you can vary the draft, which is the depth at which they are into the water, and so that you can also vary the power input and the velocity they impart to the flow. So the good thing is that they will give velocity to the lagoon. The ditch requires the motion back and forth all the time. However, the problem is they're cooling a lot the water and the release of odors and aerosols. And this is an example. You see the rotor could be lifted out of the water when not needed and goes partially in the water or go deeper in the water. And what it does is aerate immediately downstream of it, and then it doesn't aerate for the rest. So you're going to have like high DO, low DO, high DO, low DO. It's like having aerobic, anoxic, intermittent reactors with higher circulation. So it's like somewhat of like more of like a CSTR kind of arrangement if you look at the effluent patterns. And they could also be on barges. This is less common in lagoons, but this is more like legacy systems. Diffused aerations are instead the lion's share of the type of aeration systems we have in municipal applications. Coarse bubbles are now confined to mixing channels or degassing channels, where you need to reduce the amount of dissolved gas that you have in a tank. There is a mismatch in terms of depth compared to the clarifier, so much deeper than the clarifier. But in fine pore diffusers are the most common ones, and coarse bubble diffusers remain as a dominant in industrial treatment, where you have very high oxygen transfer rate requirements. Coarse bubble diffusers require little or no maintenance, and that's one of the benefits. They also have very little pressure drop. Fine pore diffusers are required to be cleaned. If you can't clean them, you should never specify them. They need to be cleaned on average once every 2 years. That's a very gross simplification, but based on observation on hundreds of tanks, we can say with confidence that once every 2 years is necessary. Some tanks with long SRT foul a little less, so maybe you could extend it a little bit more, but not by much. And after that, you will reach a plateau, the lowest possible efficiency you can have. And again, you can have different arrangement for coarse bubbles. They don't have to be full floor configuration. Their efficiency is much lower than a fine bubble. And the best efficiency is when you have full floor coverage. If you have only one side or 2 rows on the edges, when you have that what's called a ridge furrow kind of flow pattern or spiral roll, you have the least amount of efficiency. And these are the type of known full floor configuration I was mentioning. They are very inefficient. In a lot of legacy plants, this still exists. And these are some legacy units from the past where you had the coarse bubble system only on one side. And the benefit of this is that you could retrieve them. The arm will be in the upper position, so you can retrieve them for any maintenance. And then the maintenance will be done outside, and then you can put them in. But you can imagine the maintenance done over the rail, it's already very difficult. And this type of aeration system is very inefficient. So, plus all the issues with the elbow. In reality, a lot of the systems have been decommissioned and replaced with fine pore diffuser with full floor coverage. However, remember one thing. When the diffusers are coarse bubbles, they require little pressure. So the blowers will need little discharge pressure. So once you want to replace them with fine pore diffusers, you either change the blowers or you are limited in your options because you are limited by the blower pressure. So you either have to put them above the floor by a lot or change it to only, say, ceramic diffusers that are the lowest pressure drop for all the fine bubble diffusers. Spargers, these ones are the ones you saw on those extension arms in the previous slide, are the ones with there's a bored hole in the nipple with either one or more discharge points. And or you can have chicken feeders, so-called, because they look like a chicken trough, a chicken feeding trough. And these are the ones that are fed from one side, and the bubbles, you see there is an underwater photographs over there. The bubbles are released by the small holes, the large holes, or the slit, the very long slit. And so this type of configuration here is considered probably like a 2 cross roll configuration with those region furrow. But a full floor will have a 3rd row in the middle there, and it's not for municipal anymore, but definitely for industrial they still have market. This release a lot more air, and then the sparger, and over a larger area, of course, because they're longer, and being made of stainless steel, they're supposed to last forever practically. And then fine pore diffusers, instead, these are the ones that are dominating the municipal market, except plants like high purity oxygen that requires necessarily to have surface aerators. But the fine pore diffusers are, we call them fine pore diffuser, not fine bubble diffuser, because you can make fine bubbles also from turbines, but those are the efficiency of mechanical systems. Fine pore diffusers are the one with the pipe and the membrane, and the bubbles goes through the membrane or the sinter, either stone or plastic. And typically they are in full floor configurations on the floor or slightly above the floor, but never too much, because they mix less than other diffusers. So something can settle underneath, of course. And there is a whole catalog of materials, from ceramic to plastics to different type of rubbers, more engineered rubber, more consumer grade rubbers. And they have advantages or disadvantages. Some of them are more geographically located because the manufacturer and the distributors are more centered on a geographical area. Usually a matrix of different selection criteria should be employed when selecting diffusers for a replacement or an installation, not just the cost, because the cost of the diffuser may be irrelevant compared to the life cycle cost, because you have to have the diffuser, the replacement, the maintenance and cleaning of the diffuser, and the electricity to run them at their efficiency a long time. So that's a very important thing. And so the life cycle cost should come in as the quantitative decision factor at the end. We have different type of geometries. The old domes, now mostly defunct. We have the discs. The standard size is 9 inches, which is about, what is it, 220 millimeter in diameter. We have older 7 inches smaller, but they're largely being abandoned. And the 9-inch seem to be the industrial standard, even though it doesn't really have a reason to be exactly 9 inches. We have some that have been 12 inches, some have been 14 inches, but 9 inches have been the industrial standard for a long time. And largely because the early generation were 9 inches, and every subsequent ones they picked 9 inches for interchangeability, to use the same assembly and changing either the diffuser or membrane or the diffuser ceramic disc. But there is not really a premium to have exactly 9 inches. It just so happens to be. We could also have tubes. It could be made of membrane or ceramic, or we can have panels. Panels are only made of membranes, and panels are typically made of polyurethane nowadays, whereas tubes could be made of any rubber or ceramic or even sintered plastic, and discs same thing. So here are some pictures. Those are the old domes. The air comes in from the bottom and fills up the dome and goes through the porosity. Those had a lot of mechanical issues with the screw nipple that if made of plastic would just break and the dome will fall off. So a lot of those have been abandoned and replaced with the arrangement you see on the bottom. These are discs or ceramic in this picture, but the disc could be made of rubber. And one thing you notice, every so often there is a missing one, so you can decide how many you have, so you can use the same assembly, but you can tap close the ones you don't need, so you can have a tapered arrangement of aeration. By using the same assembly, you just choose to put less and less aeration discs to be active along the tank. And finally, on the bottom right, you have panels there. There's an operator inside the tank there that is cleaning the diffusers with a broom. Cleaning is necessary, especially for panels, because they're on the floor, and otherwise grit most likely will damage them. So that's another issue that we need to remember, to always remove grit before any aeration system. That's another issue that really plagues aeration systems. This is an assortment of some diffusers that exists, and we had in the lab for a long time, but there are also newer models. We have EPDM, PVC, EPDM of multiple formulations. We have ceramic tubes, plastic tubes, sintered plastic. We also have silicone membranes nowadays, polyurethane membranes, so a lot of more engineered rubbers existing. The pressure drop is the main characteristic of these diffusers. Remember that coarse bubble diffusers have a very low pressure drop, so it's inconsequential. It doesn't change with time because they don't foul. But fine pore diffusers have a high pressure drop when you begin, and it gets higher with time. So at some point you might run out of pressure if your blowers have a limited pressure. It's very, very important to remember that. If you have a low efficiency, you may have oxygen deficiency. But if you have low pressure, you don't excessive pressure and low pressure in the blower, you don't have bubbles coming out at all. And so some companies have marketed mechanical systems that were hybrid, so a turbine that mixes the water instead of drafting water in or splashing the droplets out. It will push the water in front of a coarse bubble diffuser, so the bubbles get sheared to be smaller. You have now two things. You have the blower and the motor for the turbine. So you have two mechanical units. The total power is the combined power of the two. So another one could be a jet aerator, where you have a pump moving in front of a nozzle. So you need to either have a draft jet aerator or a compressed air jet aerator, in which case you have two units, the pump and the blower. So this tend to be less efficient than fine pore diffusers. And turbines could be, like for example, the one on the left, it pushes down the water in front of a coarse bubble diffuser at the bottom, and then comes up. Or it could be at the top and it pushes down in front of a coarse bubble diffuser. It could be a chicken feeder, it could be a ring, okay? And he splashes it down and that shears up and comes up at the top. The left is also the arrangement that nowadays is used for hyperbolic mixer aerators. And jet aerators instead, you have usually air supply from a blower, goes into a nozzle and a pump. So you have the air come out as a jet on the horizontal part, there's very little transfer because it's saturated with oxygen, and then as it rises, it forms a plume, and that plume oxygenates, but also has the same DO pattern as a surface aerator, where the DO is exhausted with time. And finally, let's look at what we should do very quickly to do the diagnostic of an aeration system. First of all, walk the plant. Look around the plant and you can clearly see that there's a damaged diffuser when you see a little geyser of air. What happened there? Well, it's either a diffuser that fell off or there is a crack into the air distribution pipe. And what could be these cracks? You see that airline fracture below that pipe? It looks innocuous. You can barely tell it's there when you're looking at the pipe without water. But when that pipe there, that's a line there. That's the fracture there. But when the pipe is in the water, you see there's a big swell and all the air wants to come out there because it's the point of least resistance. So the air doesn't really come out from the diffusers anymore. Another issue is that you install the diffusers and they're not perfectly leveled. And you should laser level the diffusers, because the ones that are slightly higher elevation, the air will want to come out there because there is less pressure. And this is even more important when the diffusers have a low pressure drop like ceramic, because any little change will be comparable to the pressure drop of the diffuser. A higher pressure drop diffuser is less critical. But you see there is a patch there when you have poor discharge because they are not leveled properly.